The first speaker today is Professor Tamagawa from Kyoto. He will speak on torsion, abelian schemes, and rational points on moduli spaces. This is joint work with Anna Cadoret.
Thank you very much. So I'd like to start with repeating my title, Torsion of abelian schemes and rational points on moduli spaces. And this is joint work with Anna Cadoret. And for the papers on my joint papers on this subject, all the papers are available at another homepage. Now, so the title is Torsion of abelian schemes and rational points on moduli spaces. But another title or subtitle may be Galois theory and Diophantine geometry 5 for some reason. But in Kim's talk, more stress is put on this direction. He applies Galois theory to obtain fantastic results in Diophantine geometry. But in this talk, we stress more on the other direction. So usually Diophantine geometry is a very big machinery, while Galois theory is for undergraduate. So that this is not so good direction, but we have to only do this. Okay. Yes. Now I would like to state my main theorem in this talk, which is available as the abstract in the title in the web page of INI. And so the K is a field finitely generated over the rationals, namely character 0, and X is a curve, so the smooth separated, so in the scheme language, in the separated and geometrically connected but curve over K. And X, large K, is a function field, and A is abelian scheme over X. This is not an abelian scheme, but an abelian scheme. And I'm sorry, but this is the only place in which a word looking like an abelian appears. I'm sorry. And now, so I'd like to introduce one notation, x d. So d is an integer, positive integer. Then dxd is the set of point of x, which is automatically closed by the following condition, such that the degree of the residue field over K is bounded by D. Yes, for simplicity. And now, and now what is the abelian scheme? So of course, most of you know better than myself, but for also in order to prepare for the notation, I would like to explain what's this by using one blackboard. So this is namely what is the problem? What is abelian scheme over X? And this is roughly speaking a family, or even strictly speaking a family of abelian varieties with base scheme X, which is a curve. So this in particular shows that starting with this abelian scheme, we can take a generic fiber so possibly here in the United Kingdom we should write this and then we have a generic fiber. This is an abelian variety over the function field. On the other hand, for each closed point, or even not closed point, and special fiber at X, we can take a special fiber at X. Then an abelian variety A sub X over the residue field arises. And these objects are continuously deformed in this family. Yes. And on the other hand, oh, I need one more. On the other hand, if we start with any abelian variety over the function field, then we know that there exists a non-empty open subcurve of X, namely X minus finitely many closed points, and there exists an abelian scheme over U such that the generic fiber coincides with a given one. So B K equal B K. So my notation is very bad. So the B K is B K. Yes. So in this sense the notion of abelian scheme over X does not differ from the notion of abelian varieties over the function field up to finitely many points. Now continuous notations. So L is prime, and D is yes, as above, integer, positive integers. Then main theorem states as follows. So there exists an integer n depending on the all subjects, the A, X, K, and L, and also D. And then for every closed point with residual degree bounded by D, consider the fiber at X and consider the points of order power of L and rational over the base field. Then this order is bounded by N. So of course this is special case or the weak assertion for the so-called L primary torsion conjecture, strong L primary torsion conjecture, strong LTC. Strong means D is arbitrary, and the usual LTC is for D equal 1. And this is very similar statement, but there exists n only depending on K, G, L, D, and here G. What is D? So this is of relative dimension G. Then this is G dimensional, and also this is G dimensional. And in this case also, if we start G-dimensional abelian variety over the function field, then the resulting abelian scheme is of relative dimension G. Okay. And now for every K prime with degree bounded by D, and for every abelian variety, we have the following bound. So the set of order power of L and K prime rational is bounded by N. So in general, the moduli space of abelian varieties of fixed dimension and possibly fixed polarization is higher dimensional abelian varieties. But this main theorem shows that so for any one-dimensional subfamily, this strong L primary torsion conjecture holds. This is the main theorem. Okay. Now, where is the eraser? This. Oh yes. And I will give a sketch of proof of this main theorem later if this PC works by using the files and the screen. But before that, I would like to mention about a small application. Modular tower conjecture. Due to mic freeze.
The strong conjecture is not bound the dimension of the variety?
Yes, thank you very much. So here G dimensional. Thank you very much. By the way, some of you know that I have been struggling with financial application, and in fact I started preparing for this talk only three hours ago, and so that possibly my presentation may contain various silly mistakes like this. So that please feel free to point out. Now, so the modular tower conjecture. Or, if you know what is this, we can say that this is application to regular inverse Galois problem, or more precisely, this is anti-application. Whoa. Phil is angry. And and anti-application to regular vascular problem in some sense. So that the non-existence of certain solution to regular vascular problem is ensured by this conjecture. And so what is the, so I would like to present the full assertion of what we proved as a corollary of this main theorem. And first, KXL is as above. And here G, bold G, is a projective system of finite group, Gn. And each transition is surjective. And G1 and G0. This. So for simplicity, I would like to start with a trivial group. And this is a projective system of finite groups. Yes. And such that now G is a projective limit of this projective system, which is profinite group. And this admits the following diagram. The G admits an open subgroup. This is subgroup, which surjects onto ZP. Every morphisms are morphism as profinite groups. Not ZP, sorry, GL. Yes. And this is a condition for the profinite group. And then and next, G R is integers such that G is non-negative, R is non-negative, and the hyperbolicity condition holds. So this only excludes finitely many pairs, exceptional pairs. And then by this and this, we obtain modular tower, so-called modular tower, which is indeed the towers of Hurwitz spaces, as in Jordan's talk. Gn, Gr, H, G1, Gr, H, G0, Gr. And here, H, G, Gr is a certain Hurwitz space. And more precisely, coarse moduli space of G covers of curves, genus G curves with R possibly ramified point. And then by definition, so possibly ramified, and so by definition this is MGR. This is a moduli space, coarse moduli space of genus G curves with R unordered point. Or more precisely, relatively étale divisor of degree R. Now finally, I would like to introduce one thing. So Xi is a morphism, K morphism from X to the last one in the last object in the projective system, namely MGR. G0 GR. Okay. Then the corollary of main theorem, or more precisely, this is not a direct corollary of to the main theorem, but the corollary to a certain chi variant of main of main theorem. So here chi is a cyclotomic character, and the contents of the variant is this is kappa x rational. This treats kappa x rational points, but in this variant we replace this set by the subgroups of maximal subgroups of L primary torsion group on which Galois acts via cyclotomic characters. But anyway, so this is relative to the main theorem, and then there exists n depending on many things, L, G, G, R, C, such that X, O, sorry, application. So this is for simplicity. D equal only, I will only explain D equal one case, and such that X, the rational point of a scheme Xn is empty. Here, so that n, if n is sufficiently large, then this is empty. And here, Xn is defined by the fiber product X, M, G, R, H, G, N, G, R. So by pulling back from MGR to X, we have a towers of covers over X, and the nth layer is called Xn. And by the way, so this is the statement, and the original main modular tower conjecture, which is still unsolved, is stronger than this, and namely there exists n only depending on K, L, G, G, R, and such that n, if n is sufficiently large, the full bit space G, N, G, R admits no rational points. So again, the full bit space is in general higher dimensional, 3G minus 3 plus R in general, and so modular tower conjecture states that the rational points are vanishing for sufficiently higher layer of the modular tower. But our corollary only shows that if we restrict this tower on the first one-dimensional sub-towers, then the similar statement is available. Yeah.
So in the original conjecture, I vaguely remember that locally you have points for the HGN TR. Is that correct?
What do you mean by
when
locally?
you have this tower of varieties?
Do
you have points over locally?
Yes. Yeah. In general, even if we assume this, even if we assume this condition, sometimes we have local points for any member. Yeah.
And for your tower over X, you don't have examples like this.
Sure. But this is a finitely generative field, and so
Oh, this even okay. You're not on a number field. It's modular.
And so in particular, modular tower conjecture for 0, 0, 4 and 1, 1 is true. In these special cases, the modular space is one-dimensional, so that we can apply directly this corollary to the original main conjecture.
Akio, is part of the conjecture that condition that G has an open subgroup projecting onto ZL?
Yes.
That's part of the modular tower conjecture.
Yes, in fact, freeze the original formulation, the condition on this projective system is was much more restrictive.
I see.
But we realize that this is only necessary condition required. Yeah.
I think that he mainly discussed the simple.
So this is the end of my explanation. But I have to mention about the relation between regular investigator problem, which is rather tautological. But this is a modular space of covers or G covers of genus G curves. So if we take G equals 0, this is a modular space of G covers of genus 0 curves. Which is more or less close to the notion of P1. And then this corollary or modular tower conjecture ensures that for some for a restricted number R of branch points, there does not exist any rational G cover over, say, P1. Yeah, this is the contents of the Hurwitz. And on the other hand, this Hurwitz space itself is not empty, so as a geometric, so as a variety. So this means that this is a rather arithmetic result, and so of course since the pi1 of geometric pi1 of a curve is finitely generated, if R is smaller than the much smaller than the minimal number of generators of G, then of course this scheme itself is empty. But in general, even if this is, in this family we have certain property that, for example, we can take G is finitely generated, and then this is a strong arithmetic constraint rather than geometric one, trivial geometric one.
I understand that you need to have bigger and bigger L groups into the tower of groups, but I don't understand why that U must be open in G, a U which surjects in the L. Do you have an example when U is not open and then this doesn't happen?
Yes, I'll consider later. So sorry. And so I'd like to use a screen, but so how to? Possibly there should exist switch.
Knock on the door.
So what shall I do?
Something is at
something.
the-
Yes, yes, yes. Nothing. Yes, function. Okay,
One is for help.
F what? No. No, that's not. So we
No,
should-
it's working.
Oh, you can say that.
Thank you. And but okay. Can, yes.
One more time. Okay, okay.
Yes, thank you. Yes. And so for this. Yes. Oh, yes. And so next I would like to present a sketch, short sketch of the proof of main theorem. Okay. And after that, I have to clean this up and then again restart with Blackboard. So yes. So our proof of main theorem is very roughly speaking Manin's proof of based on Manin's proof of L primary torsion conjecture for elliptic curves case in 60s, but slightly more complicated. And so we start with the Galois action on the set group of L torsion points on the generic fiber of the given abelian scheme, which induces the usual L-adic representation on the Tate module. This is the Tate module of the generic fiber, and we know that this Galois representations or Galois action factors through the pi 1 of x, since A is abelian. This AK comes from the abelian scheme over x, and L is a prime number which is different from the characteristic. And then we are given a L-adic Galois representation or L-adic representation of pi 1, and let's denote by G the image of this representation. And for each L primary torsion point B, we can associate the stabilizer of V in G, which is easy to see to be open. And so by Galois theory or by fundamental group theory, open subgroups corresponds to finite étale covers or connected finite étale cover. And so this XB has a main role, plays a main role in our proof. And but this is again a curve, and so let us denote by GB the genus of XB and gamma B the gonality of XB, namely the minimal degree of the rational map from XB to P1.
Is this a geometric notion? Or?
Yes, geometric notions. This is geometric gonality. Yes, thank you very much. Now, we assume for simplicity that the generic fiber of the original, the given abelian scheme admits no non-trivial isotrivial abelian subvarieties, and we can easily remove this condition, but then the statement will be slightly more complicated, so that we put this assumption for simplicity in this lecture. And then we have a next following theorem. So if the order of the L primary torsion point of B goes to infinity, then accordingly the genus also goes to infinity. And in fact, and the theorem prime is the similar statement for the gonality of curves of XB. And in fact, if gonality goes to infinity, GV has to necessarily go to infinity. So the theorem prime is stronger than theorem. Okay. So this is for the case of modular curve. This corresponds to the gonality, the genus of x1 Ln, and this is gonality of x1 Ln, and in some sense, and so this is classically known. But we prove this for arbitrary one-dimensional family of abelian varieties, with isotriviality conditions. And now, this is a genus. This is theorem. Theorem is for genus, and so I would like to sketch the proof of theorem, namely the genus of the in some sense modular curve xb goes to infinity if the order of b goes to infinity. Okay. So first of all, our proof is group theoretic, and observe the Galois representation rho and its image G, and by using the L-adic Lie group theory sometimes. And of course, XB corresponds to an open subgroup of the Galois image, so we can apply the Riemann-Fruebis genus formula to B, and so to XB. So the genus of GB, namely the genus of XB, can be described by this Galois image and the corresponding open subgroup GB, and how the inertia subgroups of the cusps or points at infinity distribute.
I'm
yes.
confused. Is your one the geometric one or the arithmetic one?
I'm sorry. I'm so sorry. So I missed explaining something. But if the base curve, anyway, so this is base. This is base change over k bar of x. Mm-hmm. In the arithmetic problem, is that we have to conclude the dichotomy, and so either the genus goes to infinity or the base field extension occurs. And but anyway, so this is thank you. Oh yes, and so thank you very much. And, but this is for geometric fundamental groups, and then by the Riemann-Fruebis genus formula, the GB can be described group theoretically by the Galois image G and its open subgroup GB, and also the how the inertia subgroups corresponding to the points at infinity of x are distributed. And so the main point is to estimate the ramification term in the Riemann-Fruebis genus formula via the observation of the inertia groups. But here, so this is slightly complicated, but here the main ingredient is the following formula in the L-adic analytic geometry. And here this is the M self product of ZL, which can be viewed as a L-adic analytic variety, and Z is an D-dimensional L-adic analytic subset. Then Z modulo Ln, which is a projection of Z into Z modulo Ln to M. So the cardinality of this is asymptotically typically constant times L to dn. Here d is a dimension, and n is this n. Yes. And now by using this, we can estimate the contribution of each inertia groups, namely the contribution of local term. Then by using Riemann-Hurwitz formula and plus some arguments, we obtain the genus, the tendency of the genus. Yes. Quick. And proof of
So
yes.
this is all over K bar?
Yes, yes, everything
Little
is.
K bar, yeah?
Yes, thank you very much. So everything is over K bar.
Everything.
Yes, yes.
Torsion points are
Yes,
over K bar.
yes, yes. Yeah, in fact, I borrowed this slide by my talk in a few years, and so I forgot modifying some notations. I'm sorry. So this is everything here. Everything is over algebraic closure. Yeah. Now the proof of the theorem prime, namely the gonality of xb goes to infinity. This is quite complicated, and I would rather leave it to Anna's talk tomorrow. Yes. And so that, in fact, so how complicated? So this complicated, yes. And in fact, this is written. The original text file is written by Anna and compiled by Anna. And unfortunately, my PC cannot compile this diagram since it is too huge. Now, theorem implies that for sufficiently large, with sufficiently large order, xb has genus greater than or equal to 2. So the by Falting's theorem models conjecture. There are only finitely many rational points on xb at most. And then by the projective limit argument or compactness argument, if for any tower of xb, as a whole, any tower and any member of the tower, the rational point does not vanish, then we have the projective system of rational points, which contradicts to the, so namely the projective limit of such points corresponds to a single abelian varieties over a single field, and this contradicts to the so then for such abelian varieties, this L primary torsion point, rational L primary torsion points should be infinity, which is infinite, which is absurd. And the theorem similarly, by using theorem prime and also this is E is should be model rank conjecture, which is also due to Falting's, and then by using the standard technique in the Diophantine geometry, by to embed the symmetric product of x into the Jacobian, then we obtain similarly like this main theorem. So this is for main theorem for d equal 1 case, namely the rational case. Yes. Yes. And but this is for general D. Yes. So could you oh, thank you very much. now I finalized the 3 parts of my talk, which consists of 4 parts, and I'd like to turn to the last part, future direction. In fact, I'm sure that we have lots of future directions, but this is a future direction. So at the beginning of this talk, I mentioned about the L torsion conjecture, LTC, but of course, this is a weakening of the full torsion conjecture, and correspondingly to this situation, we have the our main theorem should be generalized to the full version, and which is a statement. This is a conjecture. Here, this is under the notations and assumptions on the main theorem, and but we don't use specific prime L. And then the statement is there exists n depending only on A and D, but which does not depending on a specific prime L. And then for every closed point of degree bounded by D, AX, so rational torsion points, the group of rational torsion points is bounded, uniformly bounded. So that, here it is. So here we only consider L primary torsion, but here we would like to admit all the torsion group, which is much more difficult than this.
Yeah, that's hard to see. We could lift that up a little bit.
Thank you. And just similarly as this, similarly to this, this is sufficiently strong, but still the weakening of the strong. Strong. So here we have a strong TC torsion conjecture, and this is automatically, the statement is automatically generated, and NKGD. And for every K prime with degree bounded by D, so like this, and for every abelian variety, here G dimensional abelian variety, and then the rational torsion points, the cardinality of the set of rational torsion points is bounded. Uniformly bounded, yes. Now, to try to prove this conjecture along the lines of our main theorem, the proof of our main theorem.
Excuse me, for D bigger than 1 and G equals 1, is it known? Or, I mean, for D equals 1 and G equals 1, that's a theorem, yeah?
Yes, yes. Thank you very much. Thank you very much. So
my question is, for D bigger than 1 and G is 1, is it known?
Yes.
Tell me as well.
So this is sorry.
No.
Thank you very much. So this is proved by for G equal 1, but D is arbitrary. Yes, and for k equal q, k is q bar, but it is this condition should be easily removed. Yes. And these are arbitrary, yeah. But for general g greater than 1, it is widely open. So in some sense, yes, we have some abelian scheme. Then the restriction of Meller or Mazur theorem is the fiber is one dimensional, but our restriction is base is one dimensional. Yeah, but fiber is arbitrary dimensional.
Merrell's theorem, there is a further restriction.
Pardon?
In that in Merrell's theorem, the elliptic curve should be defined over K, not over K.
Okay,
We found it over some fixed number field, but I found it over Q, so it's sort of the same.
But yeah, I don't think so.
Sorry.
Because they.
Bring it down.
I
But actually, your strong conjecture and also the other one, it's okay if you just formulate it over Q. Because just take veil this on and everything is fine if you know that. Merrell's theorem, the elliptic curve has to be defined over K.
I don't think so, because his method, what he estimated is not like this, but the k prime rational points on the modular curve, and the modular curve itself is defined over the rationals, but the k prime is so that, for example, he proved that the y1 say L k prime is empty for L sufficiently large, but this corresponds to an elliptic curve defined over k prime, and this corresponds to the E prime and B. E prime is defined over elliptic curve over defined over k prime, and B is a k prime rational torsion point, and so on. And so I'm quite sure that Meller proves this. Yeah. And by using the symmetric product, by the way. Now, okay. So to prove this conjecture, and for D equal it for simplicity, along with the proof of our main theorem, then we have to show at least if B is an order prime to, sorry, A. The generic is the torsion L torsion point. The points on the geometric generic fiber of order exactly L, and if L is sufficiently large, then just similar to Meller's statement, we have to prove that the XBK is empty. But this is very difficult, and in Mazur-Meller case, they resorted to very elaborate analysis of the arithmetic geometry of modular curves. But here we start with arbitrary curve and arbitrary family of abelian varieties. So that, well, it itself is a very interesting problem, but we don't know at the time. For the time being, we don't know how to adapt the Mazur-Meller method. But in any case, we would like to prove this. But since this is difficult, first we attack a much weaker problem, namely xbk is finite. And by Farting's theorem on the model conjecture, this is again deduced from the genus condition. And this is, of course, this follows, of course, from this assertion. So the L goes to yes. So now, so the is there any colored chalk? No. Ah, yes. Thank you very much. Yes. And so this statement is now Anna and I are investigating this statement. Just as in the theorem in my PC. And for this statement, for the present, we proved that this holds if either genus of the base curve is not 0, or the original abelian scheme has semi-stable reduction everywhere on the compactification of X, except possibly for one point at infinity. So there are in general this has so in general this has a narrow model over the compactification of X, but the narrow model has several bad fibers or non-proper fibers, and but some fiber may contain the unipotent part, but some fiber may not. Namely, some fiber is semi-abelian variety, and this the connecting component is semi-abelian variety, and this condition is there is at the most one point on which the fiber of the narrow model admits a unipotent part. Then under this or this condition, we have proved this, and this statement is again this is a statement over over K-ver, and so it is a very group theoretic statement, and but so far we have to add these extra conditions. Yes. So I stop my lecture, but my lecture is continued to another lecture tomorrow. Yes. Thank you very much.
Questions?
So, in the statement you were using close bound of the curve of degree up to d. Can you as well take a phi k prime of degree up to d in the K prime part of the curve. So if the degree was smaller than d of the residue field, allows some field extension also.
Sorry, I didn't get it. So, could you
Instead
just,
of
yes.
you take a closed path,
Yes.
then an extension of the residue field.
Yes.
So that the degree over k is
yes,
d.
yes, yeah. In fact, I chose this formulation, but this reformulation is also available. Yeah. Thank you very much. Yeah.
So I'm just curious, what if you give yourself something like Lang's conjecture? I mean, while we're sort of fantasizing about what could be true, I mean, if you were interested in this case of a higher dimensional base, like the whole,
Yes.
like something for the strong conjectures, where you're over the whole moduli of a billion varieties.
Yes.
Is there any sufficiently strong, believed by some people, conjecture that sort of gives you what you want? In other words, if you replace the use of Falting's theorem with,
so the in higher dimensional case, Lang's conjecture is a standard counterpart of Falting's theorem on the model conjecture, but unfortunately, this is unsolved. And but yes, I said that this is a future direction, but another joint work with Anna in progress is to estimate, so that we estimate, so that in the file in my PC, we estimated the genus of the towers, but in the higher dimensional base case, we also obtain such a tower. Just tautologically, XB can be easily defined, and then we are trying to prove that the Kodaira dimension goes to not to infinity, but goes to the maximum, namely the dimension. And in the surface case, we have some partial results, but still we and by resorting to the classification of algebraic surfaces, but still we have to exclude some exceptional cases which we don't we cannot settle yet. But yeah, this is about the interest question, direction. The interest is another future direction, I think. Yeah. But still, after establishing the statement for Kodaira dimension, namely which correspond to the theorem in my file, we cannot resort to the final arithmetic statement is conjecture, or conditional, conditional statement. Yes.
You have no control on these surfaces that would get some map to curvilineous at least 2 or some finite alcohol.
Yeah. Sometimes, yeah. In fact, as I said, the Kodaira dimension tendency is proved for some algebraic surfaces, but inside this we have a subcategory for which we can apply this kind of trick. But subcategory of subcategory. Yeah.
So this is looking back to the future. About the past, you mentioned Manin's result. I think this was before Falting's result.
Of course.
So is my recollection correct that he was using Demianenko's trick?
Yes, exactly. Yes. So now with Falting's result, it is very easy and quick to recover Manin's proof. But you're right. At Manin's time in 60s, the model conjecture for curves is a conjecture, and so that he proved it for a higher tower of the modular curves. And you're right.
One more question.
Again, this is sort of a curiosity question. I mean, do you think that, going back to this modular tower picture,
Yes.
Do you think this statement is likely to be true if you have a profinite group like SL2ZL or something like that, which doesn't have an open subgroup within?
Yes, this is related to your question, and so so I'll consider later for this. I don't know. So the typical of course typical example which does not satisfy this condition is this. Yes. But in this case, at least so that at least some for some subquotient or not subquotient, but for some open subgroup for this, I think we have a counterexample arising from modular curves, because the base field, so that for PS, so this is almost close to PSL2 or PGL to ZL, so that up to finite. But for this, this group is realizable by the the towers, modular curves, and yes, and since the base field extensions of modular curve tower is not so big, if we restrict to this, or so that if we use the whole of this, then the base field extension corresponds to the cyclotomic towers, cyclotomic extensions. But here, if we replace this, but if we are content with this quotient, then the base field extension does not occur, not so many. So the up to finite many, we can, yes. So for some genus and for some G and R and for some open subgroup of these, I'm quite sure that we have a counterexample to this. Yes.
But if you have rigidity, can't you construct these towers if you can find compatible rigid systems of generators? I think Volklein constructed some examples.
Yeah, I have not yet considered this. Yeah, your question. Yeah, I don't know.
This construction uses only a very specific cover.
Are you speaking or are you not speaking?
Whispering.
Yeah. In Fried's construction,
Yes.
it uses a very specific cover.
Yes.
That has the property that the silo groups of the kernel to G1 have all chronological dimension 1.
Yes.
But it's not clear that morph is from a silo group, that every silo group has that property. Not clear that you can extend such a morphism to an open subgroup.
Yeah, in Fried's case, the kernel from G to say G1 is assumed to be free pro P. Yes, free pro L. Sorry, free pro L.
More questions? Well, let's